The title is Magnetics plus Mechanics plus Nanoscale Equal Electromagnetic Future. So, Professor,
well, thank you. Hey guys, first of all, I promise this will be enjoyable. The second thing I promise you, since I know I'm standing between you and dinner, I will not go over. So I'll keep looking back at that clock to make sure I am done at least 10 till before the hour in case you want to ask some questions. Let's go over here the title. Let's just dive into it. This is the obligatory slide that I'm supposed to show you that the IEEE is actually paying for me to be here. So thank you so much, IEEE. The other thing that's sort of interesting is that you see in the audience there's a lot of physicists, a lot of electrical engineers. I don't know if you know this, but I'm a mechanical engineer. And I may be the first mechanical engineer who was ever been a distinguished lecturer. Now you'll have to figure out if that's a good thing or a bad thing after my talk. Look, what's my goal here? My goal is to try to convince each and every one of you to work in this area of nanoscale multiferroics or controlling magnetism. You may say, well, why should you be working in this area? I really think that this is the future. If you look at small-scale magnetic devices, I'm going to tell you they don't exist today. And why don't they exist is really you don't have efficient control. So I'm going to try to convince you, I'm going to show you a way to actually efficiently control things. And I'm going to say you need to be working in this area because it represents a very bright future. Now look guys, the philosophy here is that, as you heard from the previous speaker, there's a lot of problems that you must overcome. It's not up to one individual, it's up to a group of individuals to overcome those problems. So I want all the smart guys out there in the audience to actually work on this problem to make it become a reality. Now the last thing I want to say on this slide, look, I'm not here to impress you that I'm really smart, because I'm not smart. I'm lucky enough to work with a lot of smart students. I'm here to motivate you to say, look, this area is really, really cool. So let's dive in a little bit here. Look, I've got to tell you a little bit about my outline today. And what I'm going to start with is I'm going to do a little bit of motivation, and then I'm going to talk a little bit about memory stuff. But look, guys, the one thing I want you to hear about this is the next topic, I'm going to talk about motors. So when you start going down the small scale, don't get locked into memory devices. There's a lot of other magnetic devices you can make in the small scale that don't exist. Now, if I have time left over, I'll talk about some superparamagnetic control. But if I don't, I'll just skip that and I'll summarize. The bottom line, if we start out today, is if you look out throughout our world, electromagnetic devices are everywhere. In fact, that sort of forms the backbone of what we've done the last 30 or 40 years. But there is a problem there. You may say, well, what is that problem? Well, let's just go back in time. The way we control magnetic energy today is typically passing a current through a wire. Oersted discovered that, what, 200 years ago? And guys, that works wonderfully well on the large scale, right? And say, well, how efficient is that? So remember this number. It's like 90% efficient. So this is a great tool that we have. But a lot of you understand that what's the problem is if you shrink this down, this no longer works in the small scale. I mean, the motor guys have known about this for a long, long time. That's why we don't have small scale electromagnetic motors. And you may ask, well, what's the size that this technology really starts to fail? It's on the order of about 1 cubic meter, 1 cubic millimeter. Now, I don't mean that it suddenly rolls off, but you start seeing the efficiency start to plummet at that point. You may say, well, what's the solution out of this box here? Well, what I'm here to tell you today is the solution is, let's look at multiferroic materials. And you may ask, well, what is a multiferroic material? Well, it's a magical material that when we apply voltage, it actually magnetizes itself. If you look at these two pictures here, you might be going, oh, wait, what's the difference here? You got electrical energy and you got electrical energy. You're both controlling magnetism, right? Well, you're sort of right there, but there is a big difference. Here on the left, right, this is a conductor. So you have high current, but very low voltage. Over here on the right, what do you have? You have actually a dielectric. So you virtually have no current, but high voltage. So the pathway out here is don't use charge, a bunch of charges to control magnetism. Actually try to control magnetic anisotropy. So that's the pitch for you today, is to be able to control magnetic anisotropy with a voltage or an electric field. Well, let's sort of do a reality check here. Now, the slide that you have in front of you has nothing to do with magnetism, right? But let's talk about efficiency. Because that's what I'm going to try to drive home to you. Efficiency is what you should be talking about when you start talking about controlling magnetism in the small scale. Well, we have this combustion engine here. We all drive around today in cars, right? And you know what? We take gas and we convert it into mechanical energy. That's what makes our cars go from point A to point B. And you ask yourself, How efficient is those systems today? It's 20% efficient. And all of us in this room say, that's awful. We need to fix that problem if we want to really save our world and make it a greener place to live. Well, now let's look at controlling magnetism in the small scale. Now, I started this pitch saying, hey, we need to do this, but you said, well, wait, we've been doing this with memory devices for decades now. In fact, there's this approach out here, spin transfer torque, that's state-of-the-art controlled MRAM devices today. So we actually have the ability to control magnetism in the small scale. But let's do an efficiency calculation. Guys, this is a really back-of-the-envelope calculation you can do, right? Energy barrier, 50 kBT. How much energy does it take to actually overcome that experimentally? And if you do that, what you find is the energy barrier is about a half an attojoule. Today, experimentally writing that is about 100 femtojoules. Look, I'm not a smart guy. Femto and atto, I can't remember those, but my calculator, if I punch it in, can actually come up with a number. The efficiency of that process, and this is what should really drive something home. If you're out in the audience, a light bulb should be going off saying, hey, this is a really big deal. The efficiency is 0.0003%. That's today. So if you look at, we were upset about this number, guys, we should be up in arms about this number. Now look, we've known about this as a society for some time now. But the problem is we have not found a way out of this box. So I'm telling you today there is a way out of the box. The previous speaker spoke a little bit about using electric field to control magnetism. I'm a believer that's the way forward. Now let's talk a little bit about multiferroics in the different classes. So if you read papers today on multiferroics, and I'm trying to convince all of you to work in this, now look, I'm going to use multiferroics and magneto-electrics somewhat interchangeable. Now the people who are really particular, well, Greg, you're wrong there. Now, I'm going to roll over if that's fine. But let's first say we're going to talk about multiferroics or magneto-electrics. You can talk about single-phase materials, right? A single material like BFO, and that's a really popular one. But by the way, all single-phase multiferroics today, they're not that great, right? They're like antiferromagnetic and ferroelectric. Like we got a problem with controlling magnetism. So really the popular topic is composites. So that's really probably what you want to focus in on for the near-term future. Long-term future, single-phase is great. That's long-term future. But in composites, there's actually three different systems. One is charge-mediated, or you can also have heard it called BCMA. And you say, well, let's do back-of-the-envelope calculations to see how efficient that is today. Now, guys, I should have told you on the previous slide to remember one number. I wanted you to remember how much energy it took to write STT today, 100 femtojoules. And we're going to compare the same size bit that's used to write STT to these three classes. For the charge-mediated system today, and this is experimental, this is not analytical, you can reduce that to about 5 femtojoules, so almost 20-fold decrease in the amount of energy today. You don't have to wait till tomorrow, you can do that today. Now the next category is there are these groups out there working on exchange-coupled systems. And what do they do there is they take a single-phase multiferroic material and they actually exchange coupled with a ferromagnetic material. Now you can do that, and there is experimental data out there today, but then you have to do some back-of-the-envelope calculations, and you say, optimistically, what can I do today with that system? You probably can get down to about 1 femtojoule. So that's a factor of 100 times better than what we have today. Now, I started this talk off telling you one thing about myself. I'm a mechanical engineer. So look, I'm going to talk today about this third class here. And you notice it's highlighted in blue. So I'm not going to talk about these first two. I'm going to talk about a strain-mediated coupled system. Now, I'm not going to do that on this slide. I'm going to do it on the next slide. So what we have here is a strain-mediated. And what you're supposed to see in this slide is you have a ferroelectric layer, piezoelectric, and you also have a magnetostrictive or a magneto-elastic material. Now, the way this system works is quite simple. It's not really rocket science or anything. You apply an electric field to the piezo, and it strains. It strains the magnetic phase, and you induce magnetic anisotropy, and you are able to control the spin or domain state in this magneto-elastic layer. Now, guys, I've got to tell you something about this system here. First of all, let's talk about piezoelectrics today. I don't know if you know this, but they've been widely studied for the last 100 years. Do you know why? Our society likes them for sonar systems. If you go out to the medical community, they actually image wounds using piezoelectrics. If you go out to the Navy community, they use them to actually find submarines in the water. They have been perfected. If you have to ask, what's the conversion efficiency from electrical to mechanical? Do you know what that would be? About 80%. You don't have to come up with a new material. That's today. The second class is this magneto-elastic material. I don't know if you know this, but the first sonar system ever out there was a magneto-elastic material. It wasn't piezo. So the same community that actually perfected piezos also perfected magneto-elastic material. And you ask, well, what's the best magneto-elastic material you can find today, and how much energy can it convert from mechanical to magnetic? It's about 80%. Now look, I've told you I'm not a smart guy, but I know if this is 80% and this is 80%, I can use the product property relation. And what I can come up with is I can come up with an efficiency of about 60% using existing materials. I mean, I don't have to discover new material. I can go out there and buy things off the shelf today and come up with 60%. Now remember, what did I tell you? 100 femtojoules was state-of-the-art today, right? If you use this 60% number, you're down to 1 attojoule. Now that 1 attojoule is not 100 times better, it's not 1,000 times better, it's like 100,000 times better than what you're currently doing today to write memory. And that's why I'm telling you, this looks like a near-term future. Now guys, the one thing I want to tell you before I go on, I'm not going to try to convince you to get to 60%. I'm going to try to convince you at least you can get to 10% today. And even 10% is 1,000 times better. But that's today, and that's not finding anything new. So let's dive into this. But before I do, let's take a little history lesson. So we're going to take a look at, well, before I do that, we say, well, why hasn't this been done before? And by the way, guys, this understanding has been known since the 40s and 50s, right? So I didn't come up with, or my colleagues who are doing strain-mediated did not come up with this understanding. The magnetics community has known about this coupling since the 40s and 50s. And do you know what? They hated those materials. And why did they hate them? Because they caused problems when they wanted to write that bit of memory. The strain fields actually caused more problems. So they wanted materials which were not magneto-elastic. Permalloy, right? Nickel iron. They chose materials which were purposely not magneto-elastic. Now I'm telling you, actually you want to do the opposite. So why hasn't someone done this today? Well, first of all, models that actually couple the two systems really haven't been widely available. The second is actually fabricating these structures and experimentally demonstrating is really, really challenging. And finally, this is a big problem. Most people want to put it on a silicon substrate here. That silicon substrate is actually clamp the system, and that's going to prevent that strain to transfer. And if you can do all these, most of the people who are only in the memory space, they go, well, we don't even need that. Let's do something else. Now let's do a little history lesson. And I know I've got 30 to 45 minutes left, guys, and I promise I will be done. But let's see what's been done. What I want to do is I want to start off with the Curie brothers. Who are the Curie brothers? They discovered piezoelectric behavior in 1880, okay? So keep that in your mind. Coupling between electrical and mechanical energy. You may not have known this, but one of the Curie brothers, 4 years later, said, well, wait, if I have this material that can convert electrical energy to mechanical energy, maybe there's a magical material out there that convert magnetic to electrical or electrical to magnetic. That was the first time, to my knowledge, that a group actually tried to find this magneto-electric material. By the way, they were unsuccessful. Fast forward, there were people out there that says, look, this single-phase material couldn't even exist. Some researchers came along in the 50s saying, look, mathematically, yes, they can exist. Then in the 1960s, researchers in the former Soviet Union discovered chromium oxide, the first single-phase magneto-electric material that's out there. Well, that was a great discovery. What was the problem? Antiferromagnetic to electric. But the other big problem, it didn't couple a lot of energy. Fast forward to 1994, that's when someone introduced this term multiferroic. So now all of a sudden we have a new word out there. But really, that didn't start the big push. The big push occurred in 2002. Researchers at Penn State. Why is that important? If you know Penn State is really good at what, guys? Sonar transducers. They actually had PZT in the lab, and they also had Terfenol-D in the lab. They took the two materials and did nothing more than glue them together. When they glued them together, they reported a magneto-electric coupling coefficient that were orders of magnitude larger than anything reported before. that set the wheels into motion that today there's thousands of papers on that topic. You say, well, wait, that means it's a crowded field. But listen to this, guys. All the work that's been done in those thousands of papers have been done on the bulk level. And virtually all of them are about applying a magnetic field and converting that energy into electrical energy. Now, what if I'm trying to convince you today of doing the converse, applying electric field and converting it into magnetic energy? Now, a few people have tried that at the bulk, but you know what? It doesn't work that well. And you may ask, well, why doesn't it work that well? Because there's domain walls in these soft ferromagnetic materials. So when you squeeze them, you're moving domain walls around. So instead of getting any magnetic change in the external surroundings, it just kills it. So you don't see any effective magnetic change in the surrounding area. And that's what we want when we control magnetism. Fast forward to the last 5 years, you've seen a steady growth in nanoscale multiferroics. And you may ask, if you're a student or someone just getting started as a faculty member, entering a new area is always a good thing, right? So let's do a paper count. If you look at the bulk multiferroic, direct magneto-electric effect, thousands of papers, really crowded area. Now I'll go down into thin film, and I'm only focusing in on strain-mediated, where you're applying electric field controlling magnetism. Yeah, there's a few out there, hundreds. But now if you go down to single domain, get rid of those domain walls, and you're actually going to try applying electric field and actually control the magnetic state, there's only a handful of papers. So if you really want to make your mark as far as writing a great paper, this is a great area to work in. But I'm going to try to convince you it's more than just writing a great paper. You actually have the potential to do something revolutionary for society. It makes a really big impact if you can actually get that efficiency number up there. So guys, now let's go into some work. So what we're going to do is everything's going to be simple today. I won't represent it state of the art. I'm trying to tell you a story. So first of all, we're going to talk about a piezo. And most of the work you're going to see is done on a PMN PT substrate. Why did we choose that? It's single crystal. It has very smooth surface. Surface roughness is your enemy when you start getting down to small scale, right? Because what happens? Pinning of domain sites, pinning of spin states. And most of the work you're going to see today, in fact, all of it's going to be in nickel film. Now, why did we choose nickel film? It's just easy. Is it the best material? No. But remember I told you about that first sonar transducer? Do you know what it was made out of? Nickel. It's a decent magneto-elastic material. No, it's not the best. But it does work, and it's simple to put down. And what we're going to do is we're going to take this bulk piezo, we're going to apply an electric field, and we're going to try to stretch that nickel film. But let's start off with a hypothesis, okay? So if we look at the side view of this nickel film, look, it's multi-domain state here. And what you should see if you were a little ant, or let's say you had a magnetic force microscope image, as you walk from left to right, you would see this little south pole exiting the film. You would see a little north pole here, and you will see a south pole here. What we want to do is apply an electric field that stretches this film. So if you watch this here, we want to move those domain walls and actually close that path off so that we actually prevent it from exiting material. So we would have controlled magnetism in the small scale now. Well, let's try this. We're going to do this on a 100 nanometer thick nickel film. The figure on your left is an atomic force microscope image. The figure on your right is a magnetic force microscope image. For those who are unfamiliar with MFM, let's talk about it for a second. These white region here means north poles coming out of the material. These black regions here means south poles coming out of the material. So we actually have striped domain patterns in our film. Now what we want to do is we want to take that sample and apply an electric field to it. So we have 0 here. We apply 0.8 megavolts per meter. And by the way, guys, that is not a large field. That is a reasonable field. I don't think in terms of volts per centimeter, but it's on the order of kilovolts per centimeter, not megavolts per centimeter. If you look really closely and squint, you might be able to see something. But I want to leave you with an impression here. We got this wrong. And one of the reasons we got it wrong is we just tried to make stuff and test stuff. The one thing I've realized since working in this field is you really have to be guided by models. If you're not guided by some models or some predictive capability, you'll keep getting it wrong. So what we found here is you see this thickness? We chose too thick of a film. We were too far from that instability of closing that flux path off. What we later learned after we read papers is we should have chosen a thinner film. So let's do this test again. Now let's do it on a 60 nanometer thick film, not 100 nanometer. You still have these flux paths coming off the surface. You still see you have a striped domain pattern, no different than what you saw on the previous slide. But now let's go in and let's do our test. So we start off here at 0 megavolts per meter. We're going to walk from left to right and see if we can turn off that magnetic state that's exiting the material. So we apply a 0.4 megavolt per meter, a 0.8 megavolt per meter, and suddenly you see, hey, now you're starting to turn off those north and south poles by just moving the domain walls around. But what's really cool is you take the electric field off and it pops back to the original configuration. So you actually have the ability to turn that switch on and off by simply applying the electric field on or taking it off. Now in this example, we were still moving domain walls around. I said the domain walls were your enemy, and it depends on what you want to do. So let's start making a smaller sample now. So now instead of making continuous film, well, let me do one other thing here. Let's now talk about a film which is in plane, not out of plane. So the previous slide had 60 nanometer thick film. This is 35 nanometer thick film. What's the difference? Now shape and anisotropy is such that all the spins are in plane. And it sort of looks like a single domain state. The other slide I want to show you is this is the strain versus electric field on this piezo sample. That shows you how much strain is being produced. The only important thing I want to show you on this slide here is A, the electric field is not large, it's reasonable. The second thing is look at the strain level here, 0.15% or 1500 microstrain. Why is that important to you? All of you fly an aircraft, right? Do you know what the strain levels are in the aircraft you fly around in? It's on the order of 0.5%. Why am I telling you that? These strains aren't enormous. That's what we see today in our aircraft, in our cars, in our jet engines. So we are not talking about some strain level which is way out of the norm. The other thing I want to point out on this slide is we are only going to deal in linear piezoelectric theory. Why do we want linear? Because it's a more efficient process. Now for those of you who don't like looking at MFMs, let's say you just like looking at MH curves, let's look at this film that's on the surface, and let's look at the M versus H along the x-axis and along the y-axis. Now guys, once again, I'm a very simple individual. If you look at these two curves on the same exact film here, what are you supposed to see? Is you see an S shape here. That means the x-axis is a hard axis, right? You see this square here. That means the y-axis is an easy axis. That spins one y along the y-axis. Now what we're going to do is we're going to apply an electric field to this piezo, and we're going to try to rotate those spins 90 degrees. So then we're going to take this square and turn it into an S, and we're going to take this S and turn it into a square. Now I'm not going to stop as I page through this, but what you need to remember is over here we want this suddenly to end as a box, and this one suddenly to end as an S. So as we apply a larger and larger electric field, notice this S turned into a black box. Down here, this S turned into a black box. So what we've effectively done is, I apologize, this box turned into an S, and this S turned into a box. We've effectively rotated the easy axis from the y-axis to the x-axis, or rotated it 90 degrees. So we can actually control the spin states in this system. But now let's go into small scale structures. So what we're going to look here is a nickel dot, which is 2 microns by 2 microns. And now we're going to say, well, what can we do as far as controlling its magnetic state? Look at this figure down here on the left. So now it gets a little bit harder to actually see what's going on, so we're going to go to the PEAM facility, photoelectro-emission microscopy. Let me teach you something about PEAM, okay? So they shoot X-rays in, and if the X-rays are parallel with the spins, that means it's white. If the X-rays coming in are 180 degrees away from the spin, that means it's black. Now if the X-rays coming in are 90 degrees to the spin, that means it's gray. So this 2 micron by 2 micron bit of nickel actually has closure paths, goes north-south, 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 north-south. And if you look, it has a prominent easy axis along this direction. We're going to walk from the right to the left, and we're going to apply a progressively higher electric field to see what happens to those spin states. As we walk from right to left, all of a sudden we see this white region here has grown. So we have manipulated the spins. Now, what's interesting here, a lot of people like to say, well, that looks like a Landau state. It sort of does. So we popped it into a Landau state. Then if we continue to apply electric field from here to here, all of a sudden we see that this white region and black region are considerably larger now. What we've effectively done is what we showed you in the previous slide, is that we had an easy axis along this direction that now we've rotated at 90 degrees. So now we've effectively achieved our objective. But there's a problem here, guys, right? If you were out here and you were a little ant, and you say, well, can I feel any magnetic change here? The answer would probably be no, right? Why? Because you have flux closure paths. Those domain walls are your enemy. So these bits are still too large. We want to get down to maybe 100 nanometers. Now, see, this is where things start becoming a problem. If you don't know what you're doing, you're going to be here forever actually trying to make guesses on what to do. So I'm going to have to segue off into a little side state and say, well, what you really need is modeling. So what modeling do you need? Well, let's do a little background here. I don't know if you ever heard this guy, Newton, who was sitting under an apple tree and an apple hit him on the head. He suddenly said F is equal to ma. Remember that guy? Well, look, his equations have been around 1687. Look, they really work really well. That's why we have aircraft and we have cars today. So then look, if you talk to the magnetics community, well, look, they have Senator Wolford, they have LLG equations, and they've been around since the 30s and 40s. And guys, those do a pretty good job too. But what we're missing is actually a marriage between these two. Now look, you might beat me up a little bit and say, look, guys back in the 50s and 60s actually introduced magnetic anisotropy terms into Landau-Lifshitz-Gilbert, and you would be right. But what they didn't do back then is they didn't couple these two equations. It's just like saying, well, look, in elastodynamics, I'm going to take one magnetic state and say, look, I can solve all the problems. It's not that easy. Now, in the last decade, there have been a handful of papers. How many? So if you're a modeler out there, your ears should perk up, say, well, wait, this is a really fruitful area to study. There's about 10 papers out there that actually talk about solving those systems of equations. So that you have elastodynamics over here and you have LLG over here. Let's dive down a little bit more detail, okay, guys? So if this is Landau-Lifshitz-Gilbert, and let's say you all work with Landau-Lifshitz-Gilbert, and you look at the effective field term here, and you say, well, what's the effective field term divided up into? You have things like the external magnetic field, right? The exchange coupling term, the magnetocrystalline anisotropy, the DMAG, and let me pause here. This is where your ears should perk up, a magneto-elastic term. H effective, which is induced by magneto-elastic, and that's where you get those basically changes in magnetic anisotropy. What's it a function of? See this term here, U, displacement. Where does U come from? Well, that comes from elastodynamics. That's Newton. Newton said, well, hey, I can actually tell you what the variation in U is for given stress or strain fields. So these equations now are coupled. They are not independent. You've got three equations here as a function of three unknowns, right? The three M's. Down here, it effectively reduces to three equations as a function of three displacements. Now you must solve those simultaneously. Now, if you're in the audience and you're an experimentalist, you may say, well, wait, do I really need to solve all those systems of equations? Let's take a look. What we did is we tried to go out and validate a code we developed in-house. So what we did is we first modeled a nickel single domain structure. How big was the nickel? About 100 nanometers. It was on a clamp substrate, silicon dioxide. And we actually said, well, how much can we change its coercive field? And what we did is we actually went out and did experiments. So here on the left, you have an SEM image. You see those white dots? That's nickel domains. Over here on the right, you see this is MFM image. You see that white and black region? That means this one nickel dot here actually has a single domain structure. So now we've gotten rid of all domain walls. So if you're a little ant here, you actually see North Pole exiting that soft material. Now what we want to see is, does our model do any better job than the conventional approaches? So the conventional approaches are like Stone and Wolford. You also have LLG, assuming constant strain, or you have this full coupled field equation. If you go in and you plot the change in the coercive field as a function of the applied strain to that substrate, you say, well, let's look at the conventional LLG and Stone and Wolford. Look at those two. They actually agree reasonably well. Good thing there, right? But what the bad thing is, look at this black dot here. That's experimental data. The current models don't capture that. However, if you actually solve the coupled system of equations, you actually get a very reasonable response. This is why you actually have to have modeling people around to actually guide what your guesses are that you're going to make next. You may ask, well, why are they so different? It's really simple. If you go and you look at this nickel nanodot here, the first thing you'll see if you look at it from a mechanical perspective, you see these free edges here? The tractions or stresses have to vanish because it's a free edge. So basically here there's no stress, but in the middle you have uniform field. In mechanics, by the way, guys, remember I told you I'm a mechanical engineer, we call that shear lag phenomenon. We've known about that 50 years. But what's really funny is the magnetic community has the same thing. What do you all call it? Demag effect, right? What's the condition here at the free edge? The continuity of the normal of flux has to be continuous, and that actually sets up demag terms. So you actually have this thing that the magnetization rolls off, and in the middle you actually have uniform. Those two features are what adds in this small scale phenomenon. Now once you have that, now you can go back and actually make a structure and see if you can turn off magnetism in the small scale. So now this is a PMMPT sample. You see these little dots here? Those are now single domain nickel structures you saw modeled 2 slides ago. Now I got to tell you again, remember about PEM? If it's white, that means the X-ray is parallel to the spin state. If it's black, that means it's 180 degrees away. And if it's gray, that means it's 90 degrees. So our goal is to turn that dot from white to gray. Now if you'll notice here in the bottom left, you'll see a voltage counter going up. And what you'll see is if you look at this circle region here, let's get back to 0. White and black, and as you increase the voltage, all of a sudden they pop to gray. So now this is probably the first demonstration of electrical control of spin states using strain-mediated effect in a single domain structure. Now look, I started this whole presentation off with what, guys? That this you can do today. And what else did I tell you? Efficiency. Efficiency is the key. If you do the calculation here, you say, well, what's the efficiency of this system or the right energy? It's about 10 femtojoules. You may go, well, Greg, you lied to us because this was supposed to be 1 attojoule, right? Well, I really didn't lie to you. There was a problem here. If you go over here and you look at the structure that we tested, is the piezoelectric substrate was a 0.5 millimeter thick. The nickel nanodot was only about 30 nanometers thick. So what we did wrong was we chose a thick PMMPT sample. Don't do that. Choose thin film. What's the problem with thin film? You've got a clamped substrate. So let's go in. I worked with a really smart guy once again. He said, well, let's make some stuff. Thin film PZT, 500 nanometers, put it on a silicon substrate. He said, I have a way to overcome that clamping issue. So what he did, you see those 4 rectangles there? Those are electrodes. This is your single domain dot in the middle. And what he thought he could do is he could apply electric field across those 2 dots. They would raise up. If you looked at the side image, these are the electric fields. They're raising up, and it's going to stretch this line segment in between, even though this is on a clamped substrate. And from that, he can actually stretch that magneto-elastic dot. So let's go into our models and see if it's possible. So we designed this structure so you let them stabilize. The little red arrows are the spin states. You'll see these reds are the electric field. It rotates. We designed the states that this is stable. Take the electric field off, you're at 50 kBT, it's stable, and you can rotate it back and forth. And guys, by the way, this is all slow motion. How fast does that rotation actually occur? About 2 nanoseconds. The other thing you may ask, well, what's the voltage that you're using here? It's on the order of 1 volt in that thin film PZT. And now let's say, how much energy does it take? Well, the right energy of this specific system you're seeing in front of you is about 0.3 femtojoules. So that's better than anything we've taught, but it's still not 1 attojoule. You may say, well, Greg, why aren't you at 1 attojoule yet? Well, the reason we're not at 1 attojoule is because it's nickel. If you go to Terfenol-D, which is the best magneto-elastic material out there, now all of a sudden it's at 0.08 femtojoules, or 80 attojoules. You say, well, why aren't you down lower than that? You have to optimize the system. If you optimize the system, it's down to 10 attojoule. Now, the last question you should be asking is, why aren't you at 1 attojoule? And what's the answer, guys? It's quite simple. Because you have this substrate, and some of the energy is going into the substrate. It's not just going into the magneto-elastic material. So this represents about a 10% energy transfer. Now look, the next slide, you're going to see sort of a summary, but I'm not done yet. I'm going to show you something else cool. We start off with saying this is bad, this is really bad. But this approach here is 4 orders of magnitude better today. You don't have to discover a new material, but you do have to overcome a lot of headaches, and that's a really big problem. Now I have about 15 minutes left, and I don't think I'm going to get to superparamagnetism, but I do want to talk about something else. All of that was focused on memory, and I tried to tell you this isn't about memory. Memory is a really small slice of what could be done. So let's say, take a red blood cell. And let's say I just want to make a ring, and that's our blue ring here. So red blood cells about 5 microns. If you make magnetic materials into rings, basically they can form 2 states. One is a vortex state. You see the little arrows going around in a circle? This is bad. Why is this bad? If you're a little ant over here, you don't see any magnetic state. However, if you form the right system, you can actually form an onion state. So if you were actually a little ant here, this ring looks like a permanent north and south pole. Now the reason I chose a ring, there is no shape anisotropy. Now for those of you guys who work in motors, you go, wait, this has the beginning of looking like a motor, right? That basically if you clock that north and south pole around 360 degrees, you actually have a stator that you could put a rotor on. So we go in and we do a bunch of team stuff, we do a bunch of modeling, and what we do out of all of this is say, well, we draw a line here. These rings on the left don't look it. Why? They're vortex states. These rings on the right are the rings we want. They can form onion states. So take a look at those. So guys, once again, you need the modeling guys along with you to sort of guide what you're doing. Then you can go in and say, well, what do we want to test now? Well, what we want to do is we want to take this ring with a north and south pole, and what we want to do is apply an electric field and see if we can get that north and south pole to rotate 45 degrees. If we can do that, we're getting closer to a motor system. So we go in and we actually now do the test. We have the model state, do this structure here. We have an onion state. This is the north pole, this is the south pole. Electric field down here. We're going to walk from left to right. And as we steadily increase the electric field, all of a sudden, we've rotated that ring 45 degrees now. So we've successfully rotated the stator by 45 degrees. So we're that much closer now to a motor system. You may ask, well, did you do that more than one ring? And look, yeah, we did with a whole bunch of rings. And actually the model does a pretty good job of actually predicting the response. But you say, well, Greg, that's only 45 degrees. If you're really going to talk about a motor, don't you have to rotate it 360 degrees? And you'd be right. So what we have to do is now let's make a new design here. PZT thin film again, right? We want it efficient. It's still on a silicon clamp substrate. But you see these ABC? Those are electrodes now. And they're spaced every 60 degrees so that we can actually develop a clocking mechanism. So if we go in and we do this modeling, we get our onion state. We apply an electric field here. It rotates over about 45 degrees. We take the electric field off. This is stable because no shape anisotropy. And then we hit with another electric field on these two, and we get that system going an entire 360 degrees around. So that's really cool. And what's so cool about it is that you can do that at megahertz speeds. Now, why is megahertz important? Because in electromagnetic motors today, they only operate at kilohertz. So what's the difference between kilohertz and megahertz if you're talking about power density? Power density in megahertz is a lot higher. So if you can actually build this motor in the small scale, basically it'll have a higher power density of any electromagnetic motor that's out there. And you say, well, have you actually tried to test it out? So this is a ring, thin film PZT, MFM image, that's our north pole. We're going to apply an electric field on these two. We're going to rotate that over 45 degrees. And then we're going to apply another electric field on these two and actually rotate it back 45 degrees. So we can get going back and forth plus and minus 45 degrees. But once again, that's only manipulating magnetic states. Really, I said you want to actually manipulate mechanical states. So I worked with this guy out of Berkeley. His name is Jeff Oker. He came up with a really clever idea. It was based on Beach's idea out of MIT. And by the way, Beach is actually talking to you all tomorrow morning. So what Beach said is he can take these rings and he can actually trap a particle in there. But he did it with all external magnetic fields. Because you have this little lower energy wedge. This is a superparamagnetic particle that's trapped in this domain wall here. So we said, well, we can put that on our structure here and we can actually manipulate it with electric fields. I got to plant a seed here. I work with chemists also. The chemists can actually put these little ligands here on the end of this particle. It's really easy for them to do. Now, if you take that ligand and that particle and you rotate around it, to me, it actually starts looking like maybe a propeller on a little flagella that you can actually start driving through maybe the bloodstream. But let's see if we can actually do this. So what you're going to see here is an image on the left. These are the nickel rings. These are these superparamagnetic particles. And lo and behold, look, they're going around the circle. So that's the good news. The only thing I'm cheating a little bit here. And the way I'm cheating is the way we're getting this to work is sort of Beach's idea. You have these huge magnetic coils. And when I say huge, only on the order of centimeters. But these rings are only on the order of microns. So really, that's still not what we're trying to do. So what we're going to do is take a look at this image here on the right, which is actually our multiferroic. So that's our particle, that's our ring here, and we're going to steadily apply electric field, and we're going to see that we can actually manipulate that particle from state A to state B. So we can actually move these particles around, and we're that much closer to actually building a motor. Now look, I'm a big dreamer these days. The older I get, the more I dream because I don't have to do the work only the students have to do. But though, I was a big fan of, when I was a kid, working on things in medicine. So I worked with this one medical doctor who's probably the best in the world on traumatic brain injury. He pulled me aside one day and goes, Greg, really what I need to diagnose TBI, traumatic brain injury, is I need to get a little sensor in this 3-micron size vessel there. But I have no way to get there. I need some mechanism to actually get there. I get a catheter close, but I can't get it to where I want to go. Now, those in the audience who are my age, who are in the 50s, you can remember this movie called Fantastic Voyage. And actually, that's what they did in the movie. Now, for those who are younger and actually watch Magic School Bus, the same thing is true in Magic School Bus, my kids tell me. So look, Fantastic Voyage or Magic School Bus, I don't care what it is, but maybe in the future, in about 10 years plus, we'll actually have a little submarine that can go around and actually navigate to this vessel using multiferroic technology. And what's on that little submarine system there? Well, A, we have our little propulsion systems here, right? That's how it manipulates itself around. B, we have memory here. It has to be efficient because you can't carry a big battery around. And even though I'm not talking about it today, there are new ways to transmit information using this electric coupled magnetic field to actually transmit EM waves. And look, I still do have about 5 or 7 minutes left, so I am going to talk about one last topic. I only have about 4 or 5 more slides, so I'm going to slow down a little bit. But guys, look, I started off the presentation talking about thin film nickel, right? By the way, we're doing Terfenol-D now. Here we have single domain. We talked about that for the memory, even the motor device. But what happens if you go smaller than single domain? You can get down to superparamagnetism, right? Let's all agree what superparamagnetism is. All the spins in this little element are still cooperating together, right? They're pointing in one direction. The only problem is there's enough thermal energy in there that at any given time, they may be pointing in this direction, but in the next time slot, they're going to be pointing in this direction. Why do they do that? Because the thermal energy is greater than the anisotropy energy. So we said, well, wait, maybe we can electrically control anisotropy at one temperature. So we got together and said, well, we can start off with a superparamagnetic particle. We can put it on PMMPT. We can actually apply an electric field which will strain this, and we believe we could stabilize the superparamagnetic into a single domain ferromagnetic structure. So at one temperature, we can turn on and off superparamagnetic behavior. Now to do that, we made nickel particles. Once again, all this is about nickel, on the order of about 10 nanometers. Now guys, this is TEM image, and in our test sample, they are not this close. Remember those little ligands I told you about the chemists can put on the particles? They put ligands on these particles to make sure the particles were at least 2 diameters away. Why am I telling you that? You don't want dipole-dipole interaction. You want to keep them separated. So we have our particles on a PMMPT substrate, and we also have a capping layer of, I think we used platinum here. And why did we cap it with anything? To prevent oxidation, but more importantly, to provide low transfer. Let's go into some data now. M versus H curves on one sample along the y-axis here and along the x-axis here. First of all, you will see that it's isotropic, comment number 1. Comment number 2 you're supposed to see is a lack of hysteresis. I know if you see a little hysteresis there, but I'm going to show you a zero field cooling curve that shows you're right close to the blocking temperature. So this shows you have pretty much superparamagnetic at room temperature. Now let's take that same sample and apply an electric field, which applies a strain, and let's repeat these MH curves. So we apply electric field about 0.4 megavolts per meter, and notice the y-axis suddenly turns into a really nice, easy axis. The black axis, or x-axis, suddenly turns into a hard axis. So what we've done, we believe here, is popped it from a superparamagnetic state into a single domain ferromagnetic state. If you don't believe that, what we did was we did zero field cooling curves. So as you heat this up at zero field, you will see the blocking temperature where this curve peaks is right around room temperature. And that's without an electric field. With an electric field, you apply 0.4 megavolts per meter, you've shifted that blocking temperature by about 30 degrees. That's the reason you're stabilizing those magnetic spins, is you're shifting the blocking temperature is one explanation, or you're just adding magnetic anisotropy, which is now larger than the thermal instability. So you're able to pop something from superparamagnetic into single domain paramagnetic. Look guys, I've shown you, I think some really cool stuff. But I read this book recently, and it's called The Innovators. And it actually chronicles how and why computers came today. And what the author is very clear on, it had nothing to do with one individual. It had nothing to do with one group of individuals. But the reason why is that the problems that people had to overcome were so complicated, each group made an incremental progress. And the reason we have computers today is that our society in general solved a whole bunch of complicated problems that all evolved into our computers today. Now, why did I tell you that story? I believe this business of electric field control of magnetism is the same type of problem for our society. That represents a barrier for things that we can only dream about in science fiction. So that's why I'm here to try to convince all of you this is a really important topic you need to be working on. If you can make a dent in it, that's great. But if you can be one of those people that actually make the huge discovery, it can change things dramatically. Now, the other thing I want to tell you before I get off this slide, what you will find throughout history, people who made revolutionary changes typically were not in their 50s. You know how old they were? They were in their 20s. So guys, it's your age group that actually has the ability. So if you look at people like Steve Jobs and Bill Gates, when did they make their thumbprint? It was when they were in their 20s. Guys, now is the time to do it. Reach for the golden ring because you really can. And the thing there is if you can do it, you can really make something really, really big happen. So look, what I try to do today is first of all, try to convince you that this is a really important area. And even if you just want to write great papers, not make great discoveries, basically it's a cool area to be in right now. And the reason why is there's not a lot of work out there. By the way, I got my PhD in composites. Not a good area to go in because it was too crowded. So this isn't a crowded area. The other thing is remember, going into this idea with just making and testing it based on a fundamental guess, you probably won't make it anywhere. The problems are just too large. I may have made it sound simple. It wasn't simple. Each one of those old things we did took years and years worth of work. Finally, if you can get the modeling guys to fabricate things and actually see what's going on is another big challenge because now you're not at microns. You're at hundreds of nanometers or smaller. But if you can get it all right, I promise you there's a lot of cool stuff, and it's not just memory. Memory is only a very, very small component. It's not just motors. Anything that we do electromagnetism in the large scale, now thinking about doing it at the small scale. And if you can do that, I think you really can change the world. It's not trivial, it's a really big thing. Now look, when I say that, the one thing I want to end on is I told you I'm not that smart, and I'm really not. But I do have really smart people I work with, and they're the ones who actually did all the work. I just am starting to become a better and better mouthpiece. So with that, guys, I hope you enjoyed my presentation, and thank you so much.
Okay, please.
Yes.
So you talked about nickel not being the best and optimizing the shape. Is PMNPT, is that the best that's available, or is that just the convenient one?
So there's a lot of good piezoelectrics. So if you're a sonar transducer guy, and let's say you're going to build a great sonar system out there, you will probably go with PZT over PMNPT because of cost. However, if you're a medical ultrasound guy that actually wants to image really fine details, you will go to PMNPT and you don't care about the cost. So it's not a 0 or 1 that this material is better. It depends on the application and what you want to do with it. Right now, as far as piezoelectric coefficients and energy efficiency and linearity, PMNPT is the best out there.
Okay, any questions?
So you mentioned that you use Terfenol-D as a magneto-elastic thing. Is it the only restricted material that you have used so far? Or?
Oh, no. So coffee B. Coffee B is magneto-restricted. So we're working right now on a coffee B element that we're flipping at 180 degrees with PMA. We like Terfenol-D and even terbium iron 2 class of family because they have the largest magneto-elastic properties. We like coffee B because if we want to look at things in the small scale, we can actually use an MTJ junction. So that's why we like coffee B. But Terfenol-D and terbium iron 2 has better efficiencies than coffee B. But the problem with Terfenol-D and terbium iron 2, let's say you go talk to the memory guys, well, can you read it with an MTJ? There are a few papers out there on using that as MTJ, but nothing to the magnitude that you see with MGO and coffee B. So I would prefer working on other things besides coffee B and MGO, but to, let's say, see what we want to see at 100 nanometer length, that makes it coffee B and MGO an ideal test platform.
How do you make those magnetic fields?
E-beam lithography. So we can make the, okay. Was that the answer you're looking for or something more detailed than that?
What is the material?
So that material was nickel. So nickel basically, I believe it's a lift-off process. So they actually put the polymer down, go in and write the polymer with the E-beam, and then they deposit nickel. We cannot do that with Terfenol-D. And the reason you can't do it with Terfenol-D is you have to crystallize it. So with Terfenol-D, what we do is we actually put down the Terfenol-D, crystallize it. We can crystallize Terfenol-D right around 400 to 450 degrees C. Why is that important number to you? Is the memory guys don't want to go over 500 degrees C, but then we have to go in, and I forget the process, but it's removing material with some type of focus ion beam to get the ring structure. So I didn't show it, but we also have ring structures of Terfenol-D.
Any questions? Okay. Okay. So let's next Professor Carman.
Okay.